So hello everyone, I'm Angela Shakota from MDPI and I will be your host for today. Welcome to the webinar Recent Progress in Electromagnetic Medical Imaging and Sensing. Before introducing MDPI and the general sensors and of course the lineup of today's event, I would like to remind everyone here that this webinar is being recorded and the recording will be made available as soon as possible on the webinar web page. Please also note that you need to be logged into the SciForum platform in order so you can see recordings of today's webinar. MDPI is a pioneer in open access publishing and has supported the academic community since 1996. Currently, the headquarters of MDPI are in Basel, Switzerland, and MDPI as a company, as open access publisher of open access journals, has the mission to foster open scientific exchange in all forms and across all disciplines. Currently, we have 472 open access journals, including 463 peer-reviewed journals and 9 conference journals. And I'm proud to say on behalf of the company, of course, that all of our journals are supported by more than 295,000 academic experts who share our mission, our values, and of course, commitment to providing high quality service for our authors. When it comes to the journal, I currently work for Sensor Journal, and Sensor Journal is one of the organizers of today's event. It is an international peer-reviewed open access journal on the science and technology of sensors, and currently the journal is published semi-monthly online by MDPI. What's maybe more important for you as the authors is that manuscripts are peer-reviewed, and the first decision is provided to the authors approximately in 80.6 days after submission. Acceptance to publication is made in less than 3 days, and 42 days is a median processing time. So basically time from submission to publication. When it comes to the metrics of the journal, currently the impact factor of the journal is 3.4, and the journal ranks Q2 in different categories: instruments and instrumentation, engineering, electrical and electronic, and chemistry analytical, while the size score of the journal is 7.3, and the journal ranks Q1 in instrumentation category. There will be 2 presentations today of 20 minutes each. One is from Professor Dr. Francesca Vipiana, and another one is from Professor Dr. Elise Fear. And these presentations will be followed by Q&A session, which will be moderated by our webinar chair, Professor Dr. Yifan Chen. I also would like to use this opportunity just to let you know that currently in Sensors we have a relevant special issue open. So the title of the special issue is very much the same: Recent Progress in Electronic Medical Imaging and Sensing. Guest editors are Professor Dr. Chen and Dr. Wang, and deadline for manuscript submission is the end of March next year. I would like also to let you know that in case you have any questions regarding the submissions and in general this special issue, you can leave it to the Q&A box, or of course reach out to our journal editorial office after the webinar. Before we introduce our chair and invite speakers today, I would also like to let you know that if you have any questions for speakers, to feel free to post them at any time in the Q&A box. You can find the Q&A box in the Zoom menu bar at the bottom of your screen, and it would be great if you could use the Q&A option and not this chat panel for the questions to the speakers. Today's webinar is chaired by Professor Dr. Yifan Chen from University of Electronic Science and Technology of China. Professor Chen is a distinguished professor in the School of Life Science and Technology at the University of Electronic Science and Technology of China, and he has held various academic and leadership positions in top-tier universities, not just in China, but also in New Zealand, UK, and Singapore. And he is a Fellow of Engineering New Zealand, the Institution of Engineering and Technology, and the European Alliance for Innovation. Besides these responsibilities, he is also a senior editor, associate editor, and guest editor for several cross-disciplinary journals, and has chaired various conferences in the field. His research focuses on in vivo computation, molecular and biological communications, and electromagnetic biomedicine. And of course, I would like to mention that his work has received international funding and media coverage. Once again, I would really, on behalf of the journal, to thank Professor Chen for accepting our offer to chair this webinar. I also have the honor of introducing our first speaker, Professor Dr. Francesca Vipiana. She is a full professor of electromagnetic fields in the Department of Electronics and Telecommunication from Politecnico di Torino. Her main research activities concern the modeling, design, implementation, and testing of sensing systems for medical and industrial applications as well. And moreover, her research includes numerical techniques based on integral equations and the method of moments, with the focus on multi-resolution and hierarchical schemes, domain decomposition, preconditioning and fast solution methods, advanced quadrature integration schemes, and glide periodic structures. Professor Vipiana received the Lotsa Mid-Career Distinguished Award from the IEEE Antennas and Propagation Society in 2017. She was an associate editor of the journal IEEE Transactions on Antennas and Propagation from 2018 to 2024, and the founder of the Women and Engineering column in the IEEE Antennas and Propagation magazine from 2019 to 2024, and she's also founder and the chair of the EUR-AAP Women in Antennas and Propagation Working Group from 2021 to 2024, and she is the member of EUR-AAP Board of Directors and vice chair of the IEEE AAP as Diversity, Equity, Inclusion, and Sense of Belonging Committee. We will also have the pleasure of attending another session today, led by Professor Dr. Elise Fear. Professor Dr. Fear is a professor and associate head of research in the Department of Electrical and Software Engineering at the University of Calgary. She was the Alberta Innovates Technology Futures I-Core Strategics Chair in Multi-Modality Imaging and Sensing from 2030 to 2017. And her research interests include microwave imaging and sensing for biomedical applications, including the development of prototype systems and pilot feasibility studies with human subjects. Besides this, Dr. Fee's work has been recognized through the Outstanding Paper Award from IEEE Transactions on Biomedical Engineering Journal in 2007, the Killam Interdisciplinary Research Prize 2012, the Killam Annual Professorship 2018, and many more. And together with Jeremy Burick, Dr. Fear co-founded WaveView Imaging in 2020, which is a spin-off company aimed at commercializing medical microwave imaging. And this company was one of the 3 Canadian companies which were selected for Pfizer's Healthcare Hub program 2 years ago, specifically as I said, 2 years ago in 2023. So thank you very much all for joining today's webinar and for accepting to lead these sessions today. Before we begin with the sessions, I would like just to briefly mention that our journal is also actively involved in organizing 2 international conferences. These events basically serve as a platform for researchers to present their work, to connect with peers, and discuss the latest developments in the field. So to cut the long story short, this first conference is the second international conference on artificial intelligence sensors and transducers, and this one will take place in Kuala Lumpur, Malaysia, late July, early August this year. And I also put a QR code here, so in case you are interested in this, feel free to scan it and find out more information. And the another conference, the second one, is the 11th International Symposium on Sensor Science, which will be held in Barcelona, Spain, from 17 to 19 November this year. So those are the conferences our journal organizes this year. For any questions and any information regarding the journal can be found on our website, but also feel free to reach out to us after the meeting. Professor Chen, thank you very much for chairing this webinar. So this is all from my side for now. I'm handing over the floor to our chair, and enjoy everyone. Just as I see that we have raised hands, so maybe I'm not sure if Dr. Ahmed has any questions or comments. Should we discuss this maybe now, or just ask Dr. Ahmed to leave his question in the chat?
Yeah, probably we'll move on with the presentation first. Yeah.
Okay. So
yeah.
Thank you very much, and please. Okay.
Yeah, thank you, Angela. Welcome to the webinar, Recent Progress in Electromagnetic Medical Imaging and Sensing. Now, recently there have been a growing number of reports regarding EM medical imaging and sensing systems tested in clinical scenarios. Studies involving hundreds of scans have been reported, demonstrating the potential of this technology. Now, in parallel, the knowledge gained from patient scans have also driven technical innovations in hardware and algorithms, as well as practical aspects such as calibration. Now, this webinar will feature two distinguished speakers, as Angela has introduced. Now, without further delay, let's move to the first speaker, Professor Dr. Francesca Vipiana from Politecnico di Torino. The topic of Professor Vipiana's presentation today is microwave medical imaging and sensing for brain stroke monitoring. So let's welcome Professor Vipiana.
Okay, thank you for the very nice presentation, for the invitation. So I try to share the slides. Okay, so thanks again for the very nice invitation to be part of this seminar. And so I start with my part. As said, I will focus on the use of this technology, so medical imaging sensing at microwaves for, in particular, brain stroke monitoring. So before entering in the details of the technology applied to this specific medical field, I would like to give a bit of an overview of it. So first of all, which is the basics of it. So essentially, the reason because this technology can be used is that because microwaves are able to exploit differences in the electric properties that in the medical application would correspond to the different tissue. And as the electric properties, I mean the complex permittivity. So here I'm reporting as an example a microwave imaging system where we have all the antennas around the part of the body under test, in this case is the breast. And so thanks to the signal that is transmitted and received by all the antennas, it would be able to identify the possible presence of a scatter, that in this case is a tumor, and so to locate it, to estimate the dimension and estimate the kind of tissue. So which are the two fundamental data that are needed in this technology? We need to know the so-called total field, that is the field that we have with then radiating in the scenario under test. And then we need to know also the incident field, that is the field that we would have in the same scenario, but without the unknown scatter. So in the previous case is without the tumor. And the information that we really need is within the scattered field. That is the difference between the total, the incident field, that even if in this simple example, you can see it can identify the presence of some unknown scatterers. In theory, we would like to know this field everywhere in the scenario under test, but most of the time we know them only where we place our antenna. So in the previous case, as in this picture here, is already only on a circumference surrounding the scenario under test. So with this limited, very limited information, with the appropriate processing technique, we can have as an output the whole information about the scenario under test, in particular, and information of possible unknown scatter inside it. So keeping this in mind, it seems, it's not so easy and straightforward, but there are many reasons behind that can justify a strong effort in trying to further develop this technology. So I'm trying to list here the main attractive characteristics of microsensing and imaging. So first of all, we can say that it's totally safe. We use signals that are at microhertz, that means in this case a few gigahertz, at very low power. So we can say that the signal is totally safe for the patient. And the application of the technology could be real time. This is mainly related to the kind of hardware and software that is used, but it's possible to arrive to real time. The technology is in general cost efficient in the sense that in particular the transmitter and the receiver to be used are a lot developed also in other fields. As I said, will work at few gigahertz, so the cost could be very low. Is easy to operate in the sense that at the end we have an image that can allow the clinician to understand what is happening in that part under analysis of the body. And the final system could be a portable system. This is again related to the specific hardware that is used, but could be relatively small and so easy to move. As any technology, there are some intrinsic constraints. First of all, what we need to have is a so-called dielectric contrast. So in other words, if we are searching for something inside tissues, what we are searching must have a difference from the dielectric point of view, so a different permittivity with respect to the surrounding tissue. This in the frequency in which we are doing the imaging. And then what we would like to have? We would like to have a high resolution, if possible, and at the same time, a good penetration. But unfortunately, these two requirements, they require opposite frequency in the sense that to increase the spatial resolution, we have to push up the frequency. To increase the penetration, it's better to work at lower frequencies. So at the end, the compromise between the resolution and penetration depth is what should guide us in the best choice for the specific application of the frequency bandwidth. Then, to summarize a bit, I try to put here which are the four main ingredients needed, in my opinion, to realize at the end a microimaging system. So first of all, we need a problem-based design procedure specific to the problem that we are trying to solve. Then we would need a reliable and effective forward solver that is needed mainly for two reasons. As first, to do a full numerical modeling of the system, to study it, and then also in the processing technique is somehow present always inside the imaging algorithm. Then we need a specialized hardware, so again specific for the kind of imaging that we would like to do, and we need as well a model-based imaging technique. And then another important point is to design a system that then has also I would say not only an academic but also an industrial impact. We need to think that for a specific need, so something where the current imaging technique fails or are very inefficient, and so with this new technology we can propose a valid alternative. Okay, keeping all of this in mind, I enter more in details in the application of this technology that I will talk about now. So we work mainly on the use of microimaging for stroke imaging. So why that? So it's not difficult to justify. So as here you see in this slide, very big numbers, we can simply say that the stroke is the second leading cause of deaths in the world. So there are many reasons behind to try to improve the diagnosis of this disease. So I will be very brief, but I would like to summarize which are the two main kind of strokes that can appear. So we can have a so-called ischemia or an hemorrhagic stroke. An ischemia happens when we have, as this picture is trying to show, a vessel within the brain where the blood rich of oxygen is blocked and so cannot reach anymore a portion of the brain. So this portion, if it's not reached by oxygen, is that the cells there starts dying. The other case instead is an hemorrhagic stroke. An hemorrhagic stroke is instead when the vessel is broken, so the blood comes out from the vessel, and so it could be a very strong pressure on some cells of the brain, and this again will damage the brain. In both cases, the current so-called gold standard technique for imaging, to image what is within the brain, are magnetic resonance imaging and computerized tomography. I'm reporting here a couple of examples of imaging. They can be very they can be very clear, providing us information. In particular, MRI could be very detailed. But as any technique, there are some drawbacks that I'm summarizing here. So referring mainly to MRI, the image could be of very high quality, but at the same time is a technology that is in general time consuming, for sure not portable and costly. CT imaging, on the other side, is used ionizing radiation, so can be used to generate an image, but cannot be used for a long time or for repeated examination in a short time. So summarizing, both techniques can currently at least are not available in ambulance, and moreover, they are not available for a bedside monitoring of the disease. So this is the reason because many groups, like my research group, we are working in trying to find some technology that is complementary to these two gold standards. And as already mentioned at the beginning, here we propose to use as complementary technology microwaves. First of all, as I said in the general introduction, to use microwaves for some imaging application, we have to verify that we have a dielectric contrast. And this is quickly showed here in this picture at around 1 gigahertz. Later I will tell you because the interest is at around 1 gigahertz, where we compare in permittivity and conductivity the dielectric characteristic of the brain with respect to an hemorrhagic stroke, essentially blood, and an ischemic one. So as we can see, there is a difference. So there is a dielectric variation that allow us to give the possibility to apply microimaging. And then we will see then more in details the system, but essentially the general idea is to place antenna radiating and receiving around the head. Then we can ask to ourselves when is in the standard stroke protocol the right moment to use microimaging. And I'm identifying here 3 possibilities. One is to use it at the very beginning, directly in the ambulance, taking advantage that the system could be portable, to immediately identify the presence of the stroke, in particular to distinguish the kind of stroke, to understand if it is an ischemia or an hemorrhagic stroke. This is a very important information for clinicians to know which is the best treatment to be used. Or we can use when the patient is arriving to the hospital as an imaging technique, as an alternative to CT scan or MRI, if not available, for example. And the last option is to use instead as treatment follow-up. So in other words, after the first imaging, a treatment is given to the patient, and so we can use a microimaging system that is completely safe to monitor continuously what is happening essentially inside the brain of the patient, so to understand if the treatment is working properly. To give a quick overview of which are the current system at industrial level that are using microwaves for brain imaging, I'm summarizing here the three main ones. The first one is Medfield. The name of this system is Stroke Finder. This was the first proposed on the market. It's from Sweden. Is using microwaves, but is not exactly doing any imaging. It's doing some kind of classification of the signal, and unfortunately is no more on the market. So the two that are currently part of several clinical trials are these other two, one produced by Intensor that was originally a company from Austria, now is a US company, and EMVision that is from Australia. Then moving more to what we are doing at Polytechnic of Torino in this technology. So we are focusing mainly on the follow-up part. So repeating what I said before, after the treatment, after the first imaging, we want to follow up what is happening within the brain to support the clinician to the next action, in the next actions. So to better understand how the system works, I reported here very quickly the formulation behind. So essentially what we need to do are several measurements with all the antenna around the head. And so we measure in different time instant the scattering parameter. And then what we are interested in? We are interested in the variation of the scattering parameter. So we make the difference between each pair of scattering parameters at different time instant to verify if there is a change or not within the brain. And this difference of delta S here in the formula can be written as this integral expression where delta C is representing the variation of the permittivity. So essentially what we want to image. If we have a variation in the permittivity, means that something is happening within the brain. And then we need to know also the fields radiated by each pair of antennas inside the scenario under test at different time instant. If we keep the problem like this, it's a problem that is non-linear because we also don't know these two fields and ill-post. However, if we look a bit more in detail, so what we try to image, we can refer to the images here on the left. So this is this blue spot is representing our stroke, and you can see that in two different time instant. So what we want to image are not exactly the two strokes, but what we want to image is the variation between them. So this little area here that if we compare with the background scenario, so without any stroke, is very similar. So this justifies us to apply to the initial equation the so-called Born approximation. So replacing the field with the background field that is known, allowing to keep as unknown only the contrast. So in this way, the operator is linearized, so we can relatively easily invert it, for example, using a truncated singular value decomposition, and so to get what we want, the corresponding variation in contrast. Then there are several, this is the theory, then if we apply to a real system, as you know, as everybody knows, probably when you take measurement, always some inaccuracies are inside. And so there are several techniques to improve the quality of the final image or to better calibrate the system, we can say also like this. And here I'm reporting one of the techniques that we developed. In this case, essentially to improve the quality of the final image, we use a property of the system. So we know that the system is reciprocal. And we know from theory that if the system is reciprocal, means that the scattering matrix should be symmetrical. In our measurement, it's almost symmetrical, but not exactly symmetrical. And so what we can do, we can use the two halves, so upper triangular part and lower triangular part, to generate two images. The two images that you see, for example, here in the middle are very similar each other, but not identical. Then doing a bit of mixing between them, you see here the formula essentially is the average product. We get the image in the bottom, where the part where the real stroke is present is still there, and we can reduce a lot all the other parts here that are simply artifacts that they're changing on the two images. Then I was saying in the beginning that we are interested in what is happening at around 1 gigahertz, and to justify this, we can have a look here to this analysis of the transmission coefficient. This is obtained with a model of the head as a multi-layer structure with a different tissue within the head. And we can see that we have a very high, so top to 1, because here there is no losses, at transmission coefficient at 1 gigahertz, and then at higher frequency at around 4 gigahertz. So is convenient to work at 1 or at 4. At 4, if we add also the losses, then the signal is much lower, so this is inconvenient. So at the end, the best region to work in frequency for this application is at around 1 gigahertz. Moreover, you can see here on the y-axis the permittivity of the matching medium, that is the medium where the antenna is placed in or in front of the antenna, that allow to maximize the field radiating within the head, and our choice is to have something with the permittivity around 20. Then finally, this is our system that we realize in our lab. There are different components that I will quickly explain you. So we have the processing unit, that is a very simple standard laptop. Then we use a two-port network analyzer. Here you see the characteristic and the settings that we use. And then we have the antennas. The antennas are custom made by us. So we have a radiating part, and then we have this black part in front that is the matching medium. Realize you see here with the urethan rubber graphite powder to better match the antenna, so to maximize the field penetrating the head. Then we have a switching matrix that is this correlator based on solid state switching that is needed because we have a two-port analyzer and more than 20 antennas. So we need to have it in order to switch between all the antennas transmitting and receiving. And finally, there is the phantom. This is the first version of the phantom that is homogeneous in the sense that the phantom is simply a container with inside a liquid that here you see the characteristic is representing an average of the electric characteristic of the different tissue of the brain. And I will just report a few examples. Here is an imaging of this balloon that is changing inside, because what we want to monitor a scenario that is not always the same. So it's changing in time. So even in this case, an increasing of the stroke. Below you see the corresponding measured scattering matrix. And here the corresponding images that could be just a slice, or we can select the region where we have the highest contrast, so we can image the shape of the stroke. Then, as I already mentioned, we can monitor the variation. It's here where we can monitor how it's changing the volume, that in this case, again, is changing, for example, in the middle from 20 to 40 milliliters. And we can also get the corresponding sign, so to understand if we have a growing or a shrinking. And to conclude, I would like to say also a few words about the last part we are working on. So to use a more complex phantom, so a multi-tissue phantom, what we are realizing with the different technique, all the different tissue of the brain, keeping still a non-static part where we have the variation of the stroke. To realize it, we use different techniques. So some tissue realize as a mixture of urethan rubber and graphite powders. Other tissue realize using a carbon print filament. And then we keep the inner part liquid with this Triton water salt or alcohol water and salt mixture to be able to have a part where we can change the size. And this is just to show the different steps to realize the phantom with all the different tissues. And a couple of images where we verify first the capability to identify the presence of the stroke, so essentially to identify moving it within the head also with our images as well here. And then a monitoring, so where the stroke is increasing a direction, and we see as well our image, so the electric contrast increasing in that direction. And to conclude, my personal conclusion is that I think that the microwaves can be very successfully applied for this problem, so for brain stroke imaging, but there are still some open issues that we are working on. First of all, we are going on in measurements with a multi-tissue phantom that is much more realistic than the initial homogeneous one. We are also developing a custom front end, so essentially a transmitter and receiver behind each antenna to avoid cables and switching that can make our measure signal inaccurate. We are trying to improve the imaging using physics-assisted machine learning algorithm. And also we are trying to improve the calibration of the system, so to minimize the difference that we have between the measurement, so the real scenario, and the software that is partially modeling it in order to get the final image. And moreover, we are pushing for using it for a clinical trials, and this is planned within a European project in the next year. And to conclude, I have to credit all the different institutions that collaborate with Politecnico di Torino in this work. So Research Institute, a university from Italy, also foreign university from Europe and the US, and also hospital and companies that are working mainly on the improvement of the mechanical electronical part of the system. And the project, the European and national project, as well as IEEE Antenna Propagation Society that are supporting this research activity. And I thanks all the audience. Here my contacts.
Right. Thank you, Professor Vipiana. Now we'll move on to the next speaker, Professor Elise Fear from the Department of Electrical and Computer Engineering, University of Calgary. So Professor Elise Fear's presentation today will be on breast imaging with microwaves, a summary of recent work with patients and volunteers. So let's welcome Professor Fear.
Great, thank you very much. Can you see my screen?
Yes, yeah.
Okay, fantastic. Well, I'm really happy to see so many friends, colleagues, collaborators on the call today. It's great to have the opportunity to spend some time together and to discuss this very interesting research field. And I'd also like to thank Professor Vipiana for a really nice presentation and kind of laying some of that important groundwork and foundation when we're talking about work in this field. So I'd like to tell you a little about some of the recent work that my team has done, particularly in the area of breast imaging. And I thought I'd start by just situating this work. So we're at the University of Calgary, so we're in Southern Alberta. And I'd like to take this opportunity to acknowledge the fact that we work and play in the traditional territories of the people of the Treaty 7 region in Southern Alberta, and the city of Calgary is also home to the Métis Nation of Alberta, Districts 5 and 6. So I acknowledge that I have the great privilege to be a settler on this land and to work and to develop these technologies in this amazing place. Now, one of the other interesting things about the University of Calgary, we actually had last year a large cancer center, the Arthur J. Child Comprehensive Cancer Center open. So it's a great sandbox for innovation, and really looking forward to furthering our collaborations. And to that note, I also wanted to mention that this is definitely not an individual effort. I have a phenomenal team. So I'd just like to acknowledge the contributions of my many trainees over the years, as well as my collaborators, both from engineering and from medicine. I also co-founded a startup company with Jeremy Borke in 2020, Waveview Imaging, and I'd also like to acknowledge the amazing team that we have at Waveview, as well as our recent funders. So what I wanted to do today is, first of all, talk about why we need a new approach to breast imaging. And when we think about breast imaging from a kind of clinical established care point of view, there are a number of imaging modalities that are used routinely. This tends to change based on where you're located and access to technology. So in Alberta, in Calgary, women aged 45 to 74 are recommended to have screening with mammography. So a mammogram is an X-ray image of a compressed breast, and women with higher breast density, so with a greater proportion of glandular tissue in the breast, are recommended to have an ultrasound as a secondary screen. If something suspicious is detected, then a diagnostic mammogram, an ultrasound, and MRI may be used in order to obtain more information. And typically there's image-guided biopsy that would be used to investigate higher risk lesions. So that might be typically with ultrasound. When it comes to breast cancer treatment, in terms of monitoring the progress, typically women have a mammogram at least 6 months after the end of radiation therapy, if that's their treatment pathway. Women who are undergoing chemotherapy as their first line of treatment may have an ultrasound partway through. And I understand, for example, in the United States, the standard of care may skew more towards magnetic resonance imaging. So there are a number of established imaging techniques used in the breast cancer space, but I think there's still room for us to bring new techniques online. And there's certainly a lot of interest in a wide variety of different techniques, not just microwave imaging, but also optical techniques and things like quantitative ultrasound. So specifically, why are we interested in a new approach to breast imaging? Well, first of all, the incidence of breast cancer is increasing in women younger than 40. So currently, the screening program guidelines depend on, again, where you're located, but would start at age 40 or older. So there's a cohort of women who don't have access to breast imaging. We also know that breast density is a significant risk for breast cancer, but typically women don't know their breast density before a first mammogram. And it's also more challenging to detect tumors in dense breast tissue, and that's why ultrasound may be used for a second look. As I mentioned, in terms of treatment monitoring, there isn't really a point of care feedback method to provide patients with information on how their treatment is progressing on a regular basis. And finally, in Alberta and many other places, there are many rural and remote communities and populations underserved by healthcare where new technologies may be able to move the needle. So when it comes to breast imaging, as Professor Vipiana outlined earlier, what we're looking at would be a difference in microwave frequency properties, so permittivity and conductivity. And what we're showing here is a magnetic resonance image of the breast. So we're seeing fatty tissue in the darker pixels. The brighter pixels are glandular tissue. And we've essentially mapped these pixel intensities to dielectric properties. So we're looking at a permittivity map. And again, we can see that the fatty tissue tends to have lower properties and is relatively translucent to microwaves. Glandular tissue has greater properties, and we're seeing a tumor here with the highest properties. There are quite a few measurement studies in the literature looking at the properties of excised breast tissue. There are some reports indicating that this may be a bit of a pessimistic map when it comes to ability to detect tumors. And some of the recent results that we've obtained suggest that there's more potential for contrast than we're showing here. And we'll get into that in just a moment. So this idea of using microwaves to detect breast cancer is certainly not new. We're certainly also not the only team or startup company working in this space. So I didn't want to do an exhaustive overview of the literature today, but rather focus on sharing with you some of the advancements that my team has made. But again, we're certainly not the only people working on this. When we originally started looking at this idea of detecting breast cancer with microwaves, we started with a radar-based approach. So we're showing at the bottom of this slide 2 different prototypes. And you can see that we've been developing these technologies over quite a long time, and we've leveraged our learning at each of these different stages into developing next generation systems. So the original prototype that we used for radar-based imaging is shown here. We had some very interesting results, but we found that we needed patient-specific positioning, which led to the development of this prototype here, 4 degrees of freedom, so we could do patient-specific scans. In parallel, we started to investigate ways of providing more information on the tissue. So with radar-based imaging, we're looking at essentially time delays. So we have a signal propagating from one antenna to another. We need to know, based on the distance, what the time delay is, for example. So we need to come up with approaches to estimating the average properties of the tissue. We started looking at these approaches with this prototype here, which essentially had 2 antennas under a table. The woman would lie on her stomach, the breast extending through the hole in the table, and we'd measure the signals passing through the tissue. We obtained some interesting results, but wanted to come up with something that would provide us with multiple observations in a very rapid manner. So this is an array of 5 by 5 antennas that would be placed in contact with the tissue. Interesting solution. It was something that we could make truly portable. So this is a depiction of the system in a clinical scenario. And when we were using this system, we found that we were able to scan a small region of the breast. And when we worked with cancer patients, we were able to see responses that were consistent with their treatment history. So that was reported in Medical Physics a couple of years ago and motivated the development of this latest and greatest system. So this is a system that measures the signals transmitted through the breast and creates a map of the tissue, and we'll talk more about that. So you can see that we've developed a number of different prototypes. All of these prototypes were tested on human subjects. And in 2020, we established WaveView Imaging. So Jeremy Borky and I co-founded this in order to move scalable technology development forward, as well as things like regulatory pathways. So this is our microwave transmission system. And in this system, the participant places her breast on the lower plate. So that's this blue region here. And the upper plate is adjusted to contact the tissues using these black knobs. In terms of the plates themselves, we have 59 transmitting antennas and 240 receiving antennas embedded in the plates in this particular version. And we're measuring signals over the frequency range of 0.1 to 8 gigahertz. The sensors are scanned electronically using custom hardware and software. So how do we actually create images? We're essentially using a uniform plane wave model. So what we're looking at here are frequency-dependent signals that we've measured in free space, so that's in orange, and with a patient, that's in blue. So we measure in the frequency domain, and then we convert these signals into the time domain. So we're looking at the envelope of the signals here. This is our signal in air, this is our signal in tissue. And as we'd expect, the signal in tissue arrives after the signal traveling through the equivalent distance of air. When we take the difference in the time of arrival, we can use that to estimate the permittivity at a particular pair of sensors, and then we map those permittivity values onto a 2D plane in order to create an image. So that's our approach to imaging. We're not using model-based reconstruction. It's, again, looking at estimating permittivity at those different sensor pairs and mapping to create an image. Now, we validated our system using some custom phantoms. So this phantom consists of material representing fatty tissue in which we have a 1 centimeter diameter tumor model. And what we're seeing on the top is a CT scan of the phantom. So we like to ensure that what we are imaging, we really understand that the phantom's been constructed in a way that we would expect. This is the corresponding image. You can see here the lighter blue, that's the location of the phantom. And this is the 1 centimeter diameter tumor that we've detected and localized. We also took a look at the consistency of the performance of the system. So we scanned essentially a bag of water over 120 something days. We looked at the average permittivity that we calculated for this scan, and we found that the coefficient of variation was less than 1%. So we were confident that we had a very stable system. We used this knowledge in a study of looking at stability when we scan a group of subjects over time. So in this particular study, we recruited 35 women from the Calgary community. They were healthy volunteers, age 18 or older. They may or may not have had mammograms when they were available. We did access those mammograms, but that wasn't a requirement to participate in the study. And we scanned their left and right breasts at 3 different visits. So they came to my lab 3 times, and we scanned each breast 3 times per visit. So we have 9 images of each breast. And we also collected additional information about breast health and hormone-related interventions like HRT and birth control use. So this is an example of images of a volunteer with breast density A. So when we look at breast density, there are different categories described for radiographic breast density. So that's breast density calculated from mammograms. A means primarily fatty, B scattered, C heterogeneous, D is dense. So as we go from A to D, we have a greater proportion of glandular tissue. So this particular patient had density A. We'd expect to see lower property values, and the maximum scale here is permittivity of 10. And we're looking at images that we collected of the left and the right breast at these different time points. So these scans are about a week apart. And we can see that there is consistency between the right and the left breast in terms of those average properties, as well as consistency over time. And we can also see a bit of the effect of positioning. So you can see that the breast is in a little bit of a different position at the different time points. And also we see these regions where glandular tissue is essentially aligned with the sensor and may pass out of the imaging volume. So when we look at summarizing the average properties, so again, we define the region where the breast is, we calculate the average permittivity, and we did this for the cohort of 35 participants. And what we see is for all 9 scans of each breast, we typically see very consistent values for the right and the left breast. So again, we're seeing these clusters, very similar permittivity values collected at those different time points. When we see a greater spread in values, for example, participant 14, this would typically correspond to a smaller breast that's challenging to position in our system, as well as in other imaging systems like mammography. Interestingly, with volunteer 30, we had a mammogram for this participant, and you'll notice there's a shift between the properties of the left and the right breast. And when we looked at the imaging report, there was actually a difference in density, in mammographic density reported for the left and right breasts of this patient. The other thing that we can note from this plot is the fact that there's a variety of different properties. So for some participants, we're looking at permittivity in the range of 10 or lower. Other participants, we have permittivities, average permittivities up around 25. So we dug into the reasoning behind why we might see this range of permittivities. So what we're looking at here are mammograms. So those are the X-ray images of the compressed breast versus our microwave images for patients with breast density on mammograms of A, B, C, and D. So again, we're looking at fatty breasts, we're looking at increased glandular tissue, D having the densest composition. And we can note a couple of things. So these plots are all normalized to the same maximum value. And we're noticing that as density increases, that maximum value is increasing. And we're also seeing a greater proportion of the breast image with those higher permittivity values as we increase the breast density. So from the point of view of, what are we imaging with this technology, there does seem to be correlation between what we see on mammograms and the corresponding microwave image in terms of the fact that we're imaging higher properties with higher density. And we can also look at the distribution of glandular tissue on the mammograms and note the similarity between the microwave images and the mammograms. That being said, we're not directly registering these images. That's a complicated problem. I have a PhD student, Karina Butterworth, who is looking at ways of enabling this registration process. When we summarize this data for participants across a number of different studies, so this is 110 participants that we had mammograms for, we are seeing that typically as mammographic density increases, we do see increases in the average permittivity. And when we categorize those results into A, B, C, and D, we see that there is the potential to differentiate between A and D. There is some overlap between other categories, but that's certainly not unique to microwave imaging. My understanding is that occurs with mammography as well. But I think this is demonstrating the potential to use this kind of technology to get some insight into breast density. We've also used our system to look at treatment monitoring. So we've recruited a small group of participants, so we had 16 in total, who had a diagnosis of early stage or locally advanced breast cancer. These women were undergoing neoadjuvant chemotherapy. So this is chemotherapy used as a first line of treatment, so prior to surgery. And we scanned both breasts of each participant prior to each cycle of chemotherapy. So women would typically have 6 to 8 cycles of chemotherapy, 2 to 3 weeks apart, and we would scan before each of those cycles. And we would collect other information, mammograms, midpoint images such as ultrasound or MRI, tumor type and size, post-surgical pathology, and other information. So I wanted to share with you 2 case studies. And the first one is a participant with breast density of D. And what we're seeing here would be the mammogram. The cancer is located in the left breast. This is the mammogram of the right breast. This is our baseline scan. So this is prior to the start of chemotherapy. And we can note that there's an increased response in the breast with the cancer compared to the contralateral breast. And when we scan this patient over the course of chemotherapy, you can see that there are some changes in those properties. I know that scan day 3, there was a change in positioning. So the decreased properties are, we think they're due to a change in positioning rather than some change in the underlying physiology. Another case study here is a patient with breast density C. Again, we're looking at the mammograms for the breast with the cancer and the healthy breast. The baseline scan indicates that we have increased properties in the breast with the cancer compared to the contralateral breast. And again, we're following this patient over the course of therapy and noticing that the properties decrease, but there still is a difference between the breast with the cancer and the contralateral breast. So if we summarize these results, then we're looking here at the average permittivity of the breast with the cancer and the healthy breast over the time course of the patient in our study. And you'll note that we're scanning patients over about 128 days in this case, 105 days in this case. With case study number 2, you'll notice that the left breast with the cancer has elevated properties compared to the healthy breast. With case study 2, this patient actually had an incomplete response to therapy, whereas in case study 1, the response was complete. So these are very interesting results to us. We're still digging into them and summarizing the results for the cohort, but it appears that we have the potential to monitor treatment. And again, this builds on a study reported by Dr. Meany's team a number of years ago. In this case, we have the ability to scan both breasts of the patients in a fast kind of point of care manner. And just to wrap up some of the other things we're working on, 3D imaging. So this is work by Dr. Pedram Majabi, recently reported in IEEE Transactions on Medical Imaging, and we're looking at moving into 3D space with the data that we're collecting. So again, we're looking at patients with different breast densities and depicting the glandular tissue in a 3D manner. And again, when we look at our approach to breast cancer imaging, we're really digging into some of those clinical questions that I outlined at the beginning. So breast density unknown before a first mammogram, it looks like we have the potential to provide a measure of this. Challenging to detect cancer in dense breast tissues. Interestingly, our results show the potential for contrast in these denser tissues. And we're also encouraged by our results in the space of monitoring solutions for treatment. So in terms of some of the other applications, technology for rural and remote locations, Waveview Imaging is developing some truly portable solutions, and we're really excited to see the potential of those solutions. So I'll close there, and I very much look forward to an interesting discussion. Thanks, everyone.
Thank you, Professor Fia. So now we'll open the floor for Q&A. Probably we'll start with some of the questions on the question board. Yes. The first few questions maybe is to Professor Villapiña. One audience is asking, how do the air to skin barrier for microwaves can be overcome without using any liquid matching media? And also, in addition, how do the multi-layer structure of the head is being managed in terms of multiple reflection?
So yes, if keeping just the antennas in air and putting around the head, as is written by this researcher, you have a skin barrier better. Most of the field is reflected back. So it's completely true that is needed a matching medium, but there are many choices for that. One very common choice that for this specific application could be not so convenient from the practical point of view is to put a liquid all around. You can, but that could be a bit problematic. Our choice is it was one of the first slides that was showing, to use a semi-solid matching medium that is rubber that is mixed up with graphite powder that is just in front of the antenna, so that this is essentially between the skin and the antenna, and is designed so that the field radiated by the antenna is maximized inside the brain. So it's to match essentially the antenna to the head. So this is needed, but can be done in different ways.
Right. Okay. So another question is about the antenna near field optimization. Because most study has applied far field antennas directly to near field biomedical scenarios. So does this mismatch between the near field radiation pattern and the far field pattern affect the imaging accuracy? How should the antenna be re-optimized for the near field structure?
In our experience, the antenna to be used for the imaging system must be optimized in near field. So somehow the property of the antenna in far field, if as in this example, they are essentially attached to the head, is somehow useless. So we need to know what is doing the antenna in near field, so the field immediately in front of the antenna, to understand mainly if that field is really entering in the scenario to be analyzed. So to have some results, for sure, we need an interaction between the field entering in the part of the body and what we are searching. And this sometimes is a bit misleading, just looking to the scattering parameters, because you could have an external coupling, and that is not what we want. So we really need to check that there is an interaction between the field and the tissues. Instead, we don't get any useful information. The near
I
field
see.
study has to be done, even if in the optimization procedure, for sure, in my opinion.
So in terms of frequency selection, what frequency selection criteria does your team use to balance the penetration depth and resolution? You know, is there any optimal window frequency that could maximize the contrast?
This study of the frequency bandwidth is very related to the specific medical application that we would like to do. So in the specific case of the brain, there are some studies that I quickly mentioned during my presentation that essentially they model the head as a multi-layer structure, as it is a head, and considering the different permittivity and the different thickness, and then evaluating the transmission coefficient. And what is a particular results that was observed with this simple example, and then also through measurement, then even if we remove the losses, so we have ideal tissue without any losses, what happens? Happens that we have a very good penetration up to 1 gigahertz, and there is like a gap, probably due to the multi-layer structure, so some resonant effects, and then again, a good penetration, a higher frequency. Then if we add the losses, it is in the real world, higher frequency, higher, I mean 4 or 5 gigahertz, the signal that I receive on the other side of the head is 20 centimeters. So it's also small, is really very low. So depending on the receiver, but with the standard network analyzer is too low. And so we decided, but not only us, many systems for this application works at around 1 gigahertz, where we have a good penetration, and the resolution is limited by 1 gigahertz, but we have also to consider that the different tissue has very high permittivity. So this helps in the resolution.
Thanks. Right now we can move to Professor Fear. I saw that there is one audience asking about, is there any effect on the increase of cancer level by using this type of cancer detection? Aren't microwaves going to harm the, this one is about the brain cells. Okay, so probably is for both. The first one is about the cancer. Is there any effect on the increase of cancer levels by using this type of microwave detection technology? And also, will microwave harm the brain cells? That's for stroke detection. So, yeah.
Yeah, so I would say the technologies that we're developing are very low power. So with the frequencies that we're talking about with microwave frequencies, the key consideration is heating, but with very low powers that we're using, we're not concerned about heating. In terms of causing cancer, you know, my understanding is there would have to be sufficient energy to damage DNA, for example. So that's why there are concerns about X-rays. But with the technologies that we're using at those lower frequencies and very low power levels, we have the ability to scan frequently without worrying about side effects.
And so how about for Professor Repina, how about the brain detection? Is there any effect, harmful effect to the brain cells?
I mean, what the usual, this is a question that many times we received a common answer that can convince, I think, everybody, or at least it's the same situation, is using a mobile phone. So we are using essentially the transmitting power is lower, the one that we use in our system, but also in other similar systems, than the power that you have close to your head when you are using your mobile phone. So it's expected that you don't have any drawback. Then the time and the history will tell us, but probably not.
Right, thanks. Another audience is asking Professor Fear, in breast cancer detection, what is the resolution achieved in the dielectric permittivity difference?
Yeah, that's a great question. And certainly resolution is an issue with microwave imaging technologies if we're comparing to something like a mammogram, which has amazing resolution. We can detect and localize inclusions of 1 centimeter diameter and greater, as I've shown in our our preliminary results with our phantoms. And really, when we think about clinical applications, typically tumors are detected at 1 centimeter and greater. So our ability to detect tumors in that size range is clinically important.
Right. Okay. So for breast cancer imaging, permittivity correspondence is realized in a figure. So how to realize the correspondence between time of arrival signal strength and permittivity?
Yeah, so that's a good question. So in terms of the time of arrival, we're basically looking at that time delay. So it's not necessarily the signal strength. Signal strength is important so that we can detect the time of arrival reliably. If we have a lot of noise, it's difficult to identify precisely that time of arrival. So definitely when we know the time of arrival, we know the separation distance between our sensors. So that's something that we record separately. And with the time of arrival, the distance, we're able to estimate the permittivity.
Right. Okay. Now another question is the bad radiation of antennas, multipath, and noise effect measurements. So should it be considered on antenna design stage or post-processing? I guess that's a common question for both breast imaging and brain imaging. Yeah. So what do you feel about the radiation antennas, multipath, and so on?
Once.
Yeah. So
I think both, like design stage and post-processing. I'm looking at the question in the chat. So when we're thinking about antenna design, I think the best job that we can do at the design stage really takes the demands off the measurements and the algorithms at later stages. So certainly we've seen a lot of success having our sensors in direct contact with the tissue, rather than having spurious signals that are detected. So definitely looking at how we can optimize antenna design, and then looking at algorithms that help us to understand the signals as well, I think is very powerful. But the more we can do at the antenna design stage, the less demand there is on our measurement hardware.
right.
Yeah.
So yeah.
I can add that obviously what we want to minimize is quite obvious is the back radiation. So we want, as I said, to match the antenna with the head to maximize the radiation in the direction of the head, or more in general of the tissue under analysis. Another thing to keep in mind is to minimize also the coupling within the antennas, so the external coupling that we don't want, is to take under control the possible surface wave. Because if we have close by antennas, the tissue can generate on the tissue, you could have surface wave, so you have a coupling, but is again external to what we want to image, and this is very inconvenient. So this can be seen maybe in an easier way with the modeling, so with the software, numerical software, and this is something that has to be minimized. So we want to avoid coupling that are not through the tissue under analysis, because this can generate, could make more complex the imaging.
Because I saw related to this problem, there's audience asking, should we really consider to reduce the mutual coupling in head or breast imaging if we are going to use the multi-static information? Assuming we achieve a perfect mutual coupling, which is infinite small, we receive zero information from nearby antennas. So basically, perfect mutual coupling means we have very small mutual coupling. So any
my comment is depends on what we can consider at mutual coupling. Obviously, the antenna have to talk each other, because instead we have no information. But what we want as a designer of a microimaging system is that the signal that go from antenna to the other one, even if close by, is through the tissue. So what we want to minimize is not in general the coupling, obviously, but is the coupling external to the part of the body under test. So around or on. So this is a general guideline. And then how to apply depends on the antenna, depends on the part of the body, depends on the frequency, and so on, in my opinion.
right. Okay.
Agreed.
Yeah. So another question for Professor Fear. In your new system for breast imaging, do you use frequency domain approach or measuring time signals in very high sampling rates?
Yeah, great question. So we are using frequency domain measurements. I know there are other groups like Professor Popovich out of McGill who are looking at time domain solutions, but we are using frequency domain.
All right. Okay. To Professor Francesca, how can meta services improve the EM detection of gigahertz sensor?
depends how you use your meta-surface. No, okay. So we didn't use yet, at least, but I read some publication about it. So a good use of it, in my again opinion, that I saw in some papers, is to use, essentially, we would say, as a matching medium. So something to be placed in front of the antenna to maximize again the penetration, and maybe also to extend to a larger bandwidth if we want to do measurement in a bit larger bandwidths. But it's very related, obviously, to the meta surface that we would like to use. But a possible application is this one, because this is what we want. It's not straightforward to match the antenna with, I mean, the antenna is outside in air, the head has very high permittivity. So by default, all the signals would be reflected back. In particular, in the head, we have the CSF, that is a liquid that is essentially protecting the brain to external from external signals. So to go through is not so simple.
Yeah, right. Okay. So actually, I have a question for Professor Fear about the transmission-based this breast imaging system. Do you have to compress the breast when you are doing the measurement?
Yeah, that's a great question. So we do have our plates in contact with the tissue. We don't use the compression that is used in mammography. One of the reasons for that is we really are aiming to develop a comfortable system for women. One of the #1 feedback pieces we get is the fact that our imaging approach is comfortable. And I think another testament to that, I have a great team who works with our participants in all of our studies. We actually haven't had anyone drop out of our studies. And we're, for example, imaging cancer patients over about 6 months. We're having people come to the lab 3 visits. So we definitely have had very positive feedback on the comfort of the experience.
Right. Okay. All right. So any other questions? I saw that's more or less all the questions have been raised so far. Yeah. All right. Okay. So okay, we are also about running out of time. Okay, due to time constraint, Angela, are you going to say something,
yes,
or I will close
I
the...
think we can close if anyone if there are no more questions to be asked
Okay.
to our professors. I would
Right.
like, on the journal's behalf, to thank you, Professor Chen, and you also, Professor Vipiana and Fear, for your time and very interesting contributions to this topic. And I would also like to thank to our participants, and I really hope that you also found this webinar both interesting and insightful. I would also like to remind you one more time that the certificates of attendance are available for all registered participants on your SciForum dashboard, and recording of the webinar will be made available as soon as possible on the webinar web page. I would also like now to ask Professor Chen to close the webinar officially, and I really wish everyone a nice day or morning or evening whenever you are in the world. So thank you very much again.
Thank you, Angela. Yeah, I would actually like to take this opportunity to thank MDPI Census Editorial for hosting this event. And also thanks to Professor Fear and also Professor Vipiana. Thank you for your time. There's a huge time difference among 3 of us. So eventually we managed to find a common time slot, to come together. Yeah. Thank you for very insightful presentation, sharing about the research activities that you have done in your research groups. And also, I'm very grateful to all the audience, across different parts of the world. Thank you for your questions. And also, I hope that if there are any additional questions, you may contact professors directly, through emails. And I believe that you'll benefit more through all these communications. All right. Thank you very much, all, for all the time and all the sharing. Probably I'll call this a day, and I'll see you again, hopefully, very soon, in future sensor webinars. Thank you very much. Have a nice day.